In this video, I'm going to cover several common measures of variability or variation in data. So we're going to be looking at some numerical descriptive statistics, some things we can calculate about a numerical or quantitative data set that will help us understand how spread out these data points are. And so the things we're going to cover in this lecture are some easy ones, the range, something that's very easy and simple to talk about. And we'll talk about the interquartile range, the IQR, and then we will talk about the more important measures involving variation, which are the variance, the standard deviation, the standard deviation, I'll just abbreviate that for right now, and we will also talk about the coefficient of variation, CV, coefficient of variation, and then we will discuss what each of these measures mean and some of their advantages and disadvantages. So let's look at a real data set as we do this. And so I wanted to choose a data set that anybody could get their hands on if they wanted to. So let me show you what that is. We're going to be using this data set from the U.S. Department of Energy that you can find on fueleconomy.gov. And the file I'm going to download, I'll provide a link to this in the description of this video. But the data file that I downloaded here was the 2015 Green Vehicle Guide in Excel. As I said, I'll provide a link so that you can click it very easily so that you can look along at the data with us. So let's look at that data very quickly, and we're going to pick a variable that we can use. And let me zoom in to these quickly so that you can read them a little more easily. So here we have models of car, and not just models of car, but it looks like just about every variation, or every different kind of engine size and transmission type for automobiles sold in the United States. And so I think the variable that we might want to look at, just because it's interesting, might be the highway miles per gallon variable right over here. So some of these variables I'm just going to kind of collapse here so that we can zoom in and everybody can see these variables very easily here. So we're not really interested in all these things, so we can just focus on the miles per gallon, and we'll look at the models here as we go just to see what kind of car it is that we're talking about at each step of the way. So let's just get to know this data set a little bit. So as I said, we're going to focus on this variable here, highway miles per gallon. So let me color that yellow so we'll know that's the one that we're looking at. And I'll collapse another couple of these columns so it's easier for us to have a little bit of working space over here on the right side. So let me give us a little more room here. Okay, so in this data set there are 1,125 cars listed. You can see that if we go down to the bottom, it goes down to row number 1126. But since the first column are labels, then that tells us there are 1,125 cars. And it seems natural to treat this data set, since there are so many cars, and these are all for cars produced around the year 2014 and 2015, I think it's natural to consider this a population of cars instead of a sample. Let me see, I've got the caps lock on there. Population of cars. Alright, I'm going to be able to spell this eventually here. Population of cars. So, since we have probably every car and every version of every car being sold currently, there might be a few missing, but basically all of the cars in the population, we'll treat this as if it is the entire population when we're calculating some of these measures where it matters, especially the variance and the standard deviation. But let's just get started here and look at some of these numbers. So the simplest one to understand and the simplest one to calculate here is the range. And the range is simply a way of telling how spread out the data are by calculating the difference between the maximum value for highway miles per gallon, and the minimum. And so let's go back and look at the data and let's find the maximum and the minimum, and then we'll calculate the range. So in Excel, if you want to find the maximum and the minimum, there is a function for max and min, although it looks like you see these little green tabs up at the top left. I think that might be telling us here that this data is stored as text instead of as a number. Yes, number is stored as text. So let's go ahead and convert all of these to numbers. If you ever have this problem in a data set, sorry, my mouse went crazy there for a second. If you want to convert these to quantitative data, I'm going to select all these numbers. What I'm going to do on my keyboard, I have a Windows machine here, so I'm going to click in the first number, and then I'm going to hit Control Shift, hold Control and Shift at the same time, and hit the down arrow, and that will select everything down to the end. And then if we go back up to the top using the little scroll bar on the right here, then we can see the error or the problem that the number is stored as text. Click the drop down box and say convert to number. And so it's going through all of those and converting them to a number, and for some reason it is also changing the depth of my rows here. So let me see if I can fix that. Okay, now that we have all of this data stored as numeric data, and Excel will recognize it as that, we can just get the maximum and the minimum using these simple functions here, equals max, and then telling it where the data is that we want to use. Before we do that, let me go ahead and type in a quick shortcut to show you here. Let me again click on this first number, hit Control Shift and then the down arrow. That will select all of those numbers, and I'm going to take advantage of the name box. If you see where my cursor is, the name box label comes up right there. If you click in the name box here, we can give this data a name, like we'll call it HWY for highway, or we'll call it highway MPG, HWY MPG. Hit enter, and now if we want to use this data in a formula, we can just type equals max HWY MPG, and it will know what we're talking about. So the maximum gas mileage in this data set is 109. Let's find the minimum, equals MIN. And HWYMPG. And so the least efficient car in the data set is 15. So in order to calculate the range, it's just the difference between those two numbers, which is 109 minus 15, which will give us 94. And so that 94 just tells us the width of the data set from the smallest to the largest. Now, a problem with the range that sometimes is brought up is that the range is very sensitive to outliers. In other words, the range, if we have one car or just a couple of cars in there that have a very high mile per gallon or a very low mile per gallon, like this car, 109, it's going to affect the measurement of the range by a great deal. And so sometimes, if we want a measurement of the spread of a data set that is a little more robust, so this is not robust, it's very sensitive to the lowest and the highest value, a more robust measure of variation is the interquartile range. The interquartile range is just the difference between, instead of going all the way to the highest minus the lowest, we take the difference between the third quartile, I'll call that Q3, minus the first quartile, Q1. In other words, the 75th percentile minus the 25th percentile. What this does is it cuts off some of the extreme values at the top and the extreme values at the bottom, because we're cutting off the bottom 25% and the top 25%. And what the interquartile range will do is give us a measurement of how spread out the middle 50% is going to be. Now let's go find what those quartiles are and calculate this. Okay, I was able to determine that the first quartile is 24 and the third quartile is 32. And I'm not going to go through how that process, but I will put a link in the video here to my video where I talk about how do you go about finding percentiles and quartiles. But let me note that during the process of doing this, I found out that we don't really have 1,125 observations that we can work with here. We really only have 913. Now, how did I figure that out? Well, in order to find medians or percentiles or quartiles, you need to put the data in order from smallest to largest. That's what I did over here in column W. And when I did that, I found that at the end we have a lot of missing values, NAs. And also, before we get to the end, we have a lot of notations here that don't make a lot of sense to me. And I'm not going to take the time to explore it and try to figure out what the right number would be. But here, for example, for the Porsche 911 Carrera 4S, we have a highway miles per gallon of 40/93. It's hard for me to tell exactly what that's supposed to mean, so I'm just going to eliminate all of these from the data that we're considering. And so let me go ahead and, when we do these calculations later, I'm going to go ahead and highlight all these numbers that are real quantitative data that we can deal with and give them a new name. So we'll call them, I don't know, MPG data, because it'll be important that we have real quantitative data to put into formulas to calculate the standard deviation and some of these other measures. So, that being said, so the first quartile cuts off the bottom 25%, and so this says that a quarter, 25% of the cars get less than 24 miles per gallon, 75% get more than 24 miles per gallon. When we cut off the top 25% of cars, that cuts us way down from 109, the max, to 32. And this 32 miles per gallon says that 75% of cars get less than 32 miles per gallon, 25% get more than 32 miles per gallon. So the interquartile range is the difference between those two, which is only going to be about 8. So let's go back and write that down. So the interquartile range is only going to be 32 minus 24, or 8. And you see the huge difference between these two numbers. If you look at all the data, there's a difference of 94 between the highest and the lowest. But if you look at the middle 50% of data, which is going to be, you know, most of the cars that you'll see out there on the road, the difference, you know, the width, or the difference between those two, the 75th and 25th percentile, is only 8 miles per gallon. So you can see how some of these few cars that might be plug-in hybrids are really making this range a huge number, when in reality, most of the cars you're going to see are not going to be that different, that variable in what their gas mileage is. Okay, now let's get to the more important ones for statistics. Let me just try to write this with a little bit better handwriting here. The variance, and we're going to look at the variance formula here, and then we'll calculate it sort of by hand in Excel, and then we will get Excel to calculate it automatically for us. Now there are two formulas when you talk about the variance, and let me write both of those formulas down for you. So let me do that down here at the bottom. If you have all the data for the population, and that's kind of seems to be the situation we have with these cars, so the population variance, then the symbol we use for it is lowercase sigma squared. And here's what the formula looks like. It equals the sum of, take each number, which we call the xi's, subtract the mean from each number, and since we have data for the entire population, we're going to call that mu, the population mean, square it, and then divide it by how many numbers you have in your data set, which is the entire population. Now that's a little different from the formula if you have only a sample of data. So the sample variance is very similar except for one key difference. One minor difference is the symbol we use to let people know that this value for the variance is just an estimate based on a sample from a larger population, which means it's not perfectly accurate. So we call it s squared instead of Greek letter sigma squared. The top of the formula is basically the same thing. We take each number, we subtract the mean from it, but because we don't have all the data for the population, we use the symbol x bar, the sample mean. Square it. The key difference is on the denominator here, n minus 1. We use the lowercase n to denote the number of items in the sample, but the key calculation difference here is we're going to subtract 1 from the number of observations when we divide for a sample variance. Now why is that? Well, the reason is, and I'll give you a brief explanation now, and I'll make a mathematical proof video later if you're so inclined to watch such a thing, but it comes from the fact that in this formula we are using an estimate of the sample mean. Now if you use an estimate of a mean to calculate an estimate of yet something else, the variance of what the population is, right? We're calculating a sample variance to try to get an idea of what the population variance is, right? So it's an estimator. Same thing, the sample mean is just an estimate of what the true population mean is. And by using the sample mean in this calculation, what it does is biases, makes wrong, is a simple way of putting it, makes this calculation wrong if we divide by n, but dividing by n minus 1 adjusts for the fact that we're using an estimate here. So if we divide by n, which is a larger number, what you usually get are estimates that are smaller than what the real population variance is of the population you're estimating. So this is a kind of a difficult idea to really grasp in full and deeply, but that's the basic idea of what's going on. So let's go calculate the population variance for highway miles per gallon. And first we're going to do it by hand. We're going to get Excel to do this since we have hundreds of observations, but then we're going to get Excel to calculate it just to verify that what we're doing was right. So let's go over to Excel. Okay, here are those formulas so that we can see them. Before we get started, what we have to do is, for either way we were doing this formula, either if you have a sample or the population, you have to calculate the sample average. So let's calculate that for this data. So equals average, sample, or the mean, and we can type the name that I gave it, MPG data here. Oop, I didn't like that. One sec. Okay, I forgot I had to rename that due to those missing numbers. maybe I just typed the name wrong. Anyway, equals average mile per gallon data. The average miles per gallon on the highway is about almost exactly 29 miles per gallon there. So how about we just round that off and call it 29 when we're doing our calculations. So let's look at what this formula is telling us to do to calculate this population variance. It says take each number and subtract the mean from it. So let's do that in this column right here. So we'll call that xi minus the mean. And what we're going to do is just take equals that number in W2 and subtract 29 from it, since that's almost exactly 29. That'll make our answer a little off since we're not carrying all those decimal places, but we'll see. We'll compare it to what Excel gets when it does it. Now I'm going to copy that formula all the way down just by double-clicking on the fill handle here. And it's just calculating the difference between the miles per gallon and the average, okay? And now this formula says take that difference and square it. So, okay, let's do that. Let's do it in another column right here. And I'll make the notation SQ so we know we squared them. So, equals this. Here at 2, we'll square that difference. And we'll copy it down. And now this formula says what we should do with those squared differences is add them all up. So let's do that. I'll just do that right here. Equals sum. And we'll add up all those differences. And notice that when we square all of these differences, even though some of them were negative, some of the differences, once we square them, they're all going to become positive. And so a variance is always a positive number, or it could be 0. But the only way it can be 0 is if all the numbers in the data set are the same number. So variances are always positive numbers. So this is the sum right here. And then we have one last step to divide by n. We're going to divide by n if this is data, all the data from an entire population. And this is close enough with these cars, so we'll call this a population variance. We would subtract 1 from the number of cars if it was from a sample. And so recall over here that I said we had 913 cars that actually had data. And so that's what we added up. So we're going to divide by 913. So divide by 913. And when we do that, we get equals that number divided by 913, and now we have our population variance. So population variance. And we would call that a sigma squared. Now, here's the important part of any sort of calculation that you do in statistics. What does this number mean? What does the population variance of 68.82 tell us about the mileage of cars that they get on the highway? And the answer that I always tell my students, and for other statistics professors this may be slightly controversial, but in my opinion, what this population variance number means here, let me zoom in a little bit so you can see what I'm going to type very clearly. It means nothing much. Now, why do I say nothing much is what that means? Well, it's just that 68.8 or about 69, it's extremely difficult to come up with an interpretation of that number that makes any sense. The closest you could come would be to say, what did we just do there? Well, we looked at the difference between each car's gas mileage and the average. These are what we'd call deviations here. Right? So these are deviations from the mean, or differences between the number and the mean. And then we squared those deviations. And so after we squared them and we added them up, we divided by how many we had. So if these are the squared deviations, we add them up and divide by how many we have, then you could call the 68.82, you could call it the average squared deviation. Average squared deviation. that's not very satisfactory or very satisfying to me. That's what it means. But that is what it means. It's the average squared distance numbers are from average. But it's very hard to talk about that as being a number that we would care about on a daily basis. So I say, what does it mean? Nothing much. But why did we calculate the variance? Well, the whole point of calculating the variance is to take the square root of it to get the standard deviation. So let's take the square root of this number, and that really does have a very important meaning. So equals SQRT is one way to do the square root in Excel. And let me zoom in just a little more because I know some of you might be watching on a small screen. And the standard deviation, so this would be the population standard deviation, is about 8.3. So population standard deviation. That actually has a meaning. The standard deviation is what in my opinion, is the most important measurement in statistics. And when you see the word standard deviation, what I tell my students is to think about translating the word standard into meaning common, and the word deviation into meaning distance. Common distance. And what that standard deviation does is it tells us a common distance that these miles per gallons are from the average, a common distance. Now, it's not an average distance, and I want to stress that. If you calculate the average distance that numbers are from average, you're going to get a different number. It might be somewhere in the ballpark of 8.3, but it's going to be a different number. So that's why I call it a common distance, because it's not really an average. But what do we mean by common distance? Well, before I get into that, let me show you the commands to calculate these two numbers directly in Excel instead of going through this step-by-step process that we did. Now, we went through this step-by-step process to make sure that you've seen it and you kind of understand how these formulas work. But in practice, you probably don't want to be calculating these things in this clunky way, either with a calculator or doing this step-by-step like this. But you need to see it so that you can see how the formula works and get an idea of what's going on. But to do this directly in Excel, let me actually, well, I'll do it right over here. I know this is getting a little cluttered. Let me move this over here. Okay. In Excel, if you want to do it directly, then to get the variance, you can do equals VAR. Right? That's the function. And that will give you a sample variance, though. So let me make a notation there. So that would be the sample variance. If you want the population variance to just be calculated for you directly in Excel, then the formula would be equals VARP. You add a P and then you put the data in that you want to calculate the variance for. So in this case, we would want to use the VARP formula to get this number. So let's try it out and see what we get. Equals VARP. And I keep forgetting what I called that data. I think we called it, hold on, MPG data. Okay. Equals VARP, MPG data. And we get 68.822533. Slightly different than what we got right here, but not much different, because the only difference is because we assumed that the average was exactly 29 instead of slightly different. But you see there's not much difference there. So that's the population variance. If you want to get the standard deviation directly, without having to take the square root of a variance, then there are two formulas to get the standard deviation. Equals STDEV. That will give you a sample standard deviation. And if you want a population standard deviation, use the P on the end, just like we did for variance. Equals STDEV P. just wanted to type that. If you put an apostrophe in front of a formula, that will just let it stay there as text without giving you an error. So that's the population standard deviation. So that's what we wanted in this case. And again, we could just take the square root of this, or we can do it directly, equals STDEVP, and then MPG data. And of course, we're going to get something almost identical to what we got down here. Just a tiny bit of rounding error there. Now normally, when you have data, most of the time it is going to be sampled data. What we're working with in this case is kind of an exception. Now, without further ado, let's make sure we interpret this standard deviation, which is, again, the most important number that you can calculate in statistics. And let's round it off to 8.3. Let's call it 8.3 just for the sake of discussion here. What does that tell us about these cars? Let's go back to our little handout here. So we calculated that the variance was about 68. Let me get my pen here. Population variance was about 68. The color we can see, about 68, and that the standard deviation, which is just the square root, so the population standard deviation is the square root of the population variance, the positive square root of the population variance, and what we got was somewhere around 8.3. Same thing for the sample variance, except we would call it S. It would be the square root of S squared, would be S. And the interpretation would be about the same. So let's interpret it. Remember I said that the standard deviation, I want you to think about it as being a common distance. A common distance what? Let's be more specific. Well, it's a common distance that the data, whatever that is, here cars and their highway miles per gallon, this common distance data is going to be from the mean. Because a deviation, standard deviation is just how far something is from the mean. A standard deviation is a common distance.
So what do we mean by common distance to the mean? Well, let me draw you a little picture. An easy way to remember what we mean by common distance is that almost always you'll find most of your data in this common region where if we look at the center, the mean of a distribution of data, and the mean we had here was 29. And if we make a range going above this mean and below this mean, one of these standard deviations, so by that I mean we're going to add 8.3. So 29 plus 8.3 gives you about 37.3, right? And we subtract 8.3, and we go on the other side. 29 minus 8.3 is about 20.7. We've gone plus 1 standard deviation and minus 1 standard deviation, and we've got this common range. What you'll usually find is that most of your data are there. Now, even more than that, since a lot of times what we do in statistics, we look at distributions, we make a histogram, it's quite common, it's certainly not always, but it's quite common for data to have kind of a bell-shaped distribution, meaning that it's high in the center. Let me draw that again so that it's a little more like a bell-shaped distribution. The peak should be right at the mean here. If your histogram has bars that kind of have a shape like this, a bell-shaped distribution, or a bell curve, then what you'll normally find is between those two numbers, there will be about 2/3 of the data. Now, a little more specifically, we'll find usually about 68% of the data between those limits. But that's only going to be true if it has one of these bell shapes to it, and it's nice and symmetric. So usually about 2/3. Almost always you're going to find most of your data there. It's going to be extremely an unusual kind of situation if you don't have most of your data within one standard deviation. Now I'll have another video after this one where we discuss more about standard deviations and these bell-shaped distributions, but let's just suffice it to say for right now that usually you'll find about 2/3 of your data within those limits. Sometimes more, sometimes less, depending on what the shape looks like. Now let's look at our car data here and let's see what the distribution looks like, and let's see what percentage of our data is within one standard deviation between 20.7 and 37.3. So let's go back to our Excel file. Now if we go to our page here that has our data on it right here, we can see where we were doing our calculations. Let's go to a sheet here where I've made a histogram of the data. And I made this histogram with bins of 2 miles per gallon. So 15, 16, 17, 18, 19 and 20 are one bin, 21 to 22, etc. And you can see that this distribution is very skewed because it's got those cars that were outliers out there, some of those plug-in hybrids. The middle part here does kind of look like a bell, although it does look like it's kind of scrunched up on the ends. Normally a bell shape would fall off a little more gradually on the ends here. So this isn't really a bell shape, so I don't expect there to be very close to 68% there, but let's see what we actually find. So that range we were talking about was between 20.7 and 38.3. So let's look. So this is a frequency distribution over here. These are the bins, and these are the frequencies that Excel has calculated for us. If we start here at 21 to 22, and we add up all the bins that are from 21 to about 38 or 39 here. Let's see how many we end up with. Okay, so let's go up to 38 there, and let's add up those numbers. Let me move this graph out of the way here so that we can do that. So I'm going to sum all these bins, 21 up to 38. And let's see how many we get. We get 819. So there are 819 cars within one standard deviation of the average. And how many total cars did we have? We had 913. So I think we're going to have a lot more than 2/3 in this case. So equals 819 divided by 913 times 100. And yeah, we're getting close to 90% of our data within one standard deviation here. So that 2/3 is just kind of an approximate answer. Sometimes you'll find a lot more of your data within one standard deviation, as we did in this case, and sometimes you'll find a little less. But almost always you'll have most of your data in that common region. So the last topic, so again, for more about these bell-shaped distributions, I'll make another video, and I'll link to that at the end of this one after I get it made. The last topic I want to talk about is this common distance that tells us where most of the data is going to be. One other variation on the standard deviation is to calculate what we call the coefficient of variation. So the coefficient of variation. And the coefficient of variation, we don't have a fancy symbol for it like we do for standard deviation or mean. Most people will just abbreviate it as CV, coefficient of variation. And the coefficient of variation, let me just show you the formula, and then we'll interpret what it means. The coefficient of variation just says to take the standard deviation It's either a sample or a population standard deviation, doesn't matter. Divide it by the mean. Could be a population mean or a sample mean, doesn't matter. Multiply it times 100. What would that mean in this case? Well, it would tell us to take the 8.3 standard deviation, divide it by the average, which was 29, and multiply it times 100 and see what you get. And we're going to get a number like 28.6% is really how these things should be interpreted. And you see this calculation really is exactly like we're calculating a percent. And what we are really doing is calculating what percent is 8.3 of 29. If you remember, that is over of rule for calculating percentages. So this 28.6% just tells us that the standard deviation is 28.6% as large as the mean. The standard deviation is 28.6% of the mean. And it's a way to gauge how variable this data is compared to the size of the average. Now, why would that be useful or interesting? Well, let me give you a common example. The coefficient of variation is used sometimes in the world of finance to measure the variability or the riskiness of an investment. So let me give you two examples. Suppose we had two stocks. Stock A might have an average daily price, so we collect price data for the last 3 months, 6 months, or a year, and the average price during that time is, say, $10. And the standard deviation during that time is $2. Stock B has a higher average price. The average price over the last 6 months or so has been $100. But the standard deviation of stock B has been about $10. So what does this mean so far? Well, a standard deviation would tell you that commonly stock A is $2 above or below its average share price of $10. So some days it's up $2 above 10, some days it's below $2 below 10. Stock B on average is 100, but it's common for it to be $10 above or below its average price. Most of the time, in other words. This stock is within $10 of its average. Most of the time, this stock is within $2 of its average. So which stock is riskier, or which stock is safer? Well, your first reaction might be to say that stock A is safer because it's common for it to be very close to its average price of $10. But stock B, it's common for it to be $10. That's like 5 times as far away from its average. And that's true. But that's probably not what you're concerned with, because if somebody wants to invest some money, they want to invest a certain amount. Suppose you want to invest $100. If you invest this money in stock A, you're going to have to buy 10 of these shares. And if you buy 10 of the shares for a total investment of $100, then your total investment is going to be within 20, right? We're just multiplying everything by 10. But you'd buy one share of stock B, and commonly your investment would be within $10 of its average price. Now, the coefficient of variation kind of adjusts for that average, the difference in the average of the two prices. The coefficient of variation here would be 2, the standard deviation, over 10 times 100 would be 20%. The coefficient of variation of stock B would be 10 over 100 times 100 is 10%. And the coefficient of variation clearly tells you stock A's price commonly is within 20% of its average. Stock B's price is most commonly within 10% of its average, meaning that stock B could be interpreted as being a safer stock, a less variable price stock in that way. And you can only see that very easily by adjusting for how big the average is. And so that's what the coefficient of variation does. So I'm going to end this video now. If you have any questions or comments, please leave them in the comment section below. And in the next video, we'll look at some different types of distributions and the standard deviation, and look at picturing standard deviations with looking at histograms and talking about what percentage of the data is within a certain number of standard deviations.